In this video, we are going to go through how to take the information we've learned in regards to sketching sinusoidal relations, as well as developing the equation for sinusoidal relations, and we're going to put that all together into application problems, where we'll kind of put everything together here in one type of question. All right, so you're going to start with a word problem. So this is just kind of a plan, but it's not really anything written in stone, but you're just going to basically look for key pieces of information. You're going to use those key pieces of information to get a sketch drawn. That's going to be our first goal. Once we get a sketch drawn, then we're going to develop an equation to model the sketch that we've drawn. First example I've got involves a Ferris wheel. Basically, these questions are going to involve anything that can model a sinusoidal pattern. And I think I have 4 examples that I'm going to go through for you here. So the first one with this Ferris wheel, we're talking about a Ferris wheel. It's got a radius of 20 meters. It rotates once every 40 seconds. Passengers get on a seat that is 1 meter above ground level. How high above the ground would a passenger be situated 3 minutes and 17 seconds after starting this ride? All right, so I'm just going to, for this one, maybe draw the Ferris wheel. You don't have to do this in each question, but just to get you started. So we have a Ferris wheel. Let's see what I can come up with here. So the Ferris wheel is something like that. Some measurements now. So it said they get on 1 meter above the ground. So from here to here, that should let me, I'm just going to kind of try and make some dots here. This spot here should be at the 1 meter mark. This is how high above they are. How high above the ground they are. So this is their height in meters, and on this scale I'm going to put time in seconds. What else do we have? The Ferris wheel's got a radius of 20. Well, think of it like the unit circle. So we're going to be concerned with here. We're going to kind of map their path around, figure out where they are when they get here. Then we'll do a height reading when they get here, and then I'll do another height reading when the person gets over here, and then they'll be back to where they started with. If they start here, and the wheel has a radius of 10 meters or 20 meters, the radius is 20 meters. So from here to here is 20 meters, and then from here up to here is another 20 meters. Well, if from the ground to here would be the same as a radius is 20, and from here to here is 1. If they're right in the middle of the wheel, they should be 21 meters above the ground. If that person then comes all the way up to here, they would be situated 20 to get to the middle, then another 20 to get to the ground, and then another, sorry, not to the ground, to get to the bottom of the wheel, and then another 1 to get to the ground. So from the ground all the way up to here should be 41 meters. That would be the highest they ever get above the ground. The closest they ever get to the ground is 1. Halfway around, they're at 21. Halfway around on this side, which of course would be the same height, would also be at 21. So now, that looks after the height scale. What they told me is that the wheel makes 1 revolution every 40 seconds. So what we're concerned with is how long does it take this wheel to go around once? So 1 revolution per 40 seconds. Well, I'm just going to put 40 out here then. And like when we did trig graphs, I'm going to cut that into 4 equal parts, which means halfway around the trip should be 20 seconds. Half of that would be 10. So now you've got this scaled off. And we're basically going to now imagine that a person got on this wheel, and we're going to map their path and put a dot where they would be for each one of their stops using, let's go with something that we can see here. Nice. All right, so they're going to start here. 1, 2, 3, 4. We're going to put those 4 dots on the graph where they would fall. So at the beginning, time 0, that's where they would be. This would be a quarter of the way around their trip, which would be 10 seconds. Should be another dot there. Halfway around their trip. Halfway around their trip. 3/4 of their way around their trip. 30 seconds. They should be at a height of 21. And then when they finally finish one full turn, that should be 40 seconds in, they should be back to where they started. Now, look at these dots. Yes, they look like they might make the shape of a nice upside down V or the roof of a house. We're giving you the benefit of the doubt at this point in the unit that will let you just use these few points, but make sure your graph models a sinusoidal pattern. So I'm going to connect these now as best I can with a graph. And there we have my graph. Okay, so that's the first thing you do. You interpret all the key information out of the question. You set up a y-axis. You set up an x-axis. This scale is generally going to be time. This axis is generally going to be a height or a distance or some kind of a measurement of some sort. The next part of the question is to now take, like we did on the last assignment, and come up with any equation you want that would describe the graph that you see in front of you. So you remember what we always did first is once we had a graph, we got the sinusoidal axis. Let's put that on here. So there's your sinusoidal axis. So right away, there's 2 pieces of information that we should be able to develop very quickly. The amplitude and the vertical shift. So the vertical shift is up 21. The amplitude, which is how far is it from the middle up to there, or from the middle down to the bottom. In this case, that's 20. So the amplitude is 20. And the vertical shift is 21. A real common mistake students do here is they look at this graph and say, oh, it's moved up 1. They go to the bottom of the wave instead of the middle of the wave. Remember, your vertical shift always goes to the middle of your wave. It's tied in with your sinusoidal axis. The period. Now, these are not going to be angles in these questions. They're going to be times or some kind of measurements beside angles generally. So what I'm going to do here is figure out my K value. Well, this graph starts the pattern at 0, and it would be finished the pattern when it gets to 40. Well, that's the period. The period is 40 seconds. At this point, you get to choose, are you going to work in radians, or would you prefer to work in degrees? Again, this is a word problem. It's an application. It's completely open to you. You're the one deciding on a solution. I'm more comfortable in degrees, so I'm going to go with 360 over K equals the period. Now I'm going to rearrange and solve this for K. So 360 is equal to 40K. 360 over 40 is equal to K. So 9 would be the K value. Now, we get to pick a phase shift to go with any trig function we want. On the assignment, I was asking you to specifically find a sine function and a cosine function for each of those graphs that I gave you. It is now completely wide open and you get to choose. So if it were me doing this question, based on my 4 patterns, this graph, if you look at it, starts at a low point at 0, up to a high point, back to a low point. Well, that's the exact pattern of negative cosine. So if I was allowed to choose any trig function for this one, I would choose negative cosine. You don't have to. I'll show you if you don't choose that one, but that's the one that I would pick. And here's what my equation would look like. Y equals negative, amplitude is 20, going to go with cosine. K value is 9. Now I don't need a phase shift. Now, some students just out of habit keep putting theta here, but really these aren't thetas anymore. In this question, it would make more sense if I put t there for time. There is no phase shift, so I can close that, and my vertical shift is up 21. Student B might say, just to show you what I mean, y equals, and you see if you agree with this would also be right. I'm going to go 20 sine 9 t, but to be a sine pattern, I'd have to go to there, where it goes up, down, back to the middle. So a sine pattern is moved to the right 10 units, minus 10. If you wanted to go positive cosine, you could, but your phase shift would be right 20. You could go negative sine, and your phase shift would be right 30. Hopefully you've kind of got the hang of how that phase shift bit works now. All right, so that's the next part of the problem. Develop a graph, build a function, any function you want, then typically they'll ask you some question that you're going to now use that function to give an exact answer for. So what they want to know is, where's the person going to be situated on their trip around the Ferris wheel 3 minutes and 17 seconds after the ride starts? Well, my scale here, my variable t, stands for time, which is along here. The time they gave us was 3 minutes and 17 seconds. So what we're going to have to do is figure out what would that be in seconds alone. So 3 minutes and 17 seconds. Well, 3 times 60 is 180. This is 197 seconds. So essentially, what would happen is this graph, as the Ferris wheel kept going around and around in circles here, this graph would go over and over and over. You'd keep making that same pattern. So when the scale reached 197, what I want to figure out is, where would I hit the graph? What would be the height over here? Well, what we're going to do is use our function and substitute t equals 197. So I'm going to come over here to my function, and I'm going to substitute 197 where the t is. So y equal, I'll use the top one, minus 20 cosine brackets 9. Just change up the colors for emphasis here. This is going to be 197. That's going in for t plus 21. Now at this point, you need to have enough calculator skill to be able to input this all at once on your calculator. One thing to keep in mind here, when I created my function, I used 360 here, which means I'm talking degrees. Make sure your calculator is set to degree mode. If you had chosen to put 2 pi here, which you very well could have, it would be fine. Now k wouldn't be 9 anymore. K would be 2 pi over 40. Then you'd have to make sure your calculator's in radians. Either way, we would get the same answer. Okay, so I'm going to take my calculator. I'm just going to pause this while I punch this in my calculator. Save some video length here and see what I come up with. All right, so after typing that in my calculator, I came up with the answer. Y equals, y equals 3 point. Now remember the rule, if they do not go evenly, we are going to carry 3 decimal places. It is 3.1798, so it's going to round off to 3.180. That would be a height above the ground in meters. So we want to make sure that that answer makes sense based on our graph. What I mean by that is, I've seen students build some function here that they've messed up or type it in their calculator wrong and give me an answer like 75.3. And I said, well, there's no way that's correct, because the highest they ever get is 41 and the lowest they ever get is 1. So your answer you come up with has got to be somewhere between 41 and 1, which our answer is. All right, so there is your first look at an application problem of a sinusoidal relation. Get that off of there. All right, on to the next one. This keeps disappearing on me. All right, our next problem, something similar. Rather than a Ferris wheel, we're talking about a bicycle wheel. And this bicycle wheel gets a tack stuck in the bottom of the wheel as they're driving along. And we are going to map out the path. So let's assume there's a tack right there, gets stuck in the wheel, and that tack is now going to travel around the wheel as the bike travels down the road. That tack's going to spin round and round in circles, and we're going to map out its path on the graph. Well, let's get some key information here. The lowest point is obviously going to be here when it hits the ground and picks up the tack. The wheel has a radius of 32. So from there down to there, 32, which means the middle of this graph will be at 32. When the tack gets up to the top of the wheel up here, that'll be another 32. So the top point should be 64. All right, so this one will go from 0 to 64. This will be the height in centimeters. Now you gotta watch your time here. It's measured in milliseconds. It doesn't really matter as long as we know what the units are. 500 milliseconds. So that's how long it takes to go around once. Cut that in half. Cut that in half. That in half. So this would be 500. This would be 250. And now remember, just like the last one, so we're going to get the path followed by the tack, assuming we pick it up here, here, there, there. Those are going to be the heights we measured the tack. So let's assume that the wheels picked up the tack. There we go, started. A quarter of the way around, it should be at 32. There's a quarter of the way, 32. Halfway should be at the highest point, 64. 3/4 of the way should be back at 32. And finally, back here again, it should just touch the ground again, the tack. Make a sinusoidal wave, not a rooftop. So sinusoidal wave as best you can. And back up like so. There we have our graph. Once we have our graph, build a function. Sinusoidal axis goes in the middle. There's your sinusoidal. Okay, like last week now, so we should be getting quick at these. It's up 32. From the middle to the top, that's your amplitude. It would also be 32. The period, so it takes 500 milliseconds. So I'm going to go in degrees again. 360 over K equals 500. K is equal to 500 over 360. Now here's something really important. If these don't go evenly, leave it as a fraction. Don't say, oh, it went out to a decimal, but I rounded it off. The thing with it is, if you get something moving extremely, extremely fast, spinning in a circle, and you round this value off, it's going to make your measurements off by significant amounts just because of think of these 500 milliseconds. That's really fast. So if you kind of round that off and your substitutions in here for your time, this is going to be making 500 waves in 1 second. So that ever so slight amount that you might round this off to is going to make a difference on where you fall on that wave as you're mapping out where the tack is. So I'm going to check it on my calculator just to see what I come up with. So 500, divide that by 360. and here's an example. So I do not want it's like 1.38 whatever. So I'm going to take this and reduce it. Actually, you don't even have to, just leave it exactly like that if you want. Now it clearly reduces to 50 over 36. You could reduce that then to 25 over 18, but even if you just left it like this for the sake of calculation, that would be fine. Much like the last one, you're going to find in a lot of these ones, because a lot of times the path that you plot out starts at the bottom of some kind of a circular pattern, goes to the top, back to the bottom, which models a negative cosine. Often we're going to go with negative cosine, which I'm going to pick again this time. So here would be my function. Y equals negative 32, that's the amplitude. I'm going negative cosine. K is the reduced version of that. Doesn't go evenly, don't round it off to a decimal. It'd be 25 over 18. There's your K value. No phase shift. Vertical translation up 32. So plus 32. Question asked me, where would that tack be? 12.38 seconds. Now, I got to change that to milliseconds because my scale that I've got here for T is built on milliseconds. 12.38 seconds times, I'm in seconds, I want to get to milliseconds. There, for every 1 second, there would be milliseconds. There would be 10 to the 3 milliseconds. I'm doing that right. So now it's going to be 12,380 milliseconds in 12.38 seconds. That 12,380 milliseconds is going in here for T. Oops. Y equals negative 32 cosine 25 over 18 multiplied by the T value, which is 12,380. Close that bracket, plus 32. So we should get an answer somewhere between 0 and 64. And let's see where this tack would be at that particular instant. So again, I'll take a break here for a second. I'll put it in my calculator. All right, so putting that in my calculator, this is what I arrived at. Y equals 29.520. That would be in, I believe, centimeters. I'll double check my unit on my height scale. Yep, centimeters. So that is how high above the ground the tack would be on the wheel at that particular instant. So it's kind of neat to see that we can take what we know about sinusoidal patterns, things following a circular pattern, and take these written text, translate it into a visual graph with some numbers, go from a visual graph to a sinusoidal function. Again, don't be fooled by the word sinusoidal. That's the same word that models both sine and cosine. So sometimes students say, well, why do you keep saying cosine if it's sinusoidal? Sine and cosine are both considered sinusoidal relations. And then once you build your function, that allows you to substitute into it and determine exact values. All right, here's another one. It's a common one that sometimes students don't realize actually models sinusoidal patterns, are the ocean tides. Another one that I don't have an example of, but might be worth looking at sometime, is electricity. Electricity alternates back and forth between a positive and a negative. And if you were to examine the path of the electricity, now it's happening, mind you, very, very quickly, but it is, if you model it out through a graph, it can be modeled to follow a sinusoidal pattern. Okay, let's look at the tide question. So it says the alternating half-daily cycles of the rise and fall of the ocean are called the tides. Tides in the Bay of Fundy cause the water level to rise 6.5 meters above mean sea level and then drop to 6.5 meters below sea level. It makes this pattern every 6 hours. assume the height of the water with respect to mean sea level is sinusoidal relationship. Yep. If it's high tide at 8 a.m., determine where the water would be at 1:47 p.m. Perfect. Well, I'm going to call mean sea level right here. So, oops, 0 is what I'm going to consider to be mean sea level. This would be high tide then, 6.5 meters above. So this is the height of the water above sea level. Above sea level in meters. And low tide would be when it goes below mean sea level. So it's going to be down here at negative 6.5. Now, this is a little bit trickier in this one, this scale. It told me it makes a pattern every 6 hours. Okay, well, I'm going to say that's 6 hours. I'm going to cut that in half, say that's 3 hours. That'd be 1.5. That'd be 4.5. Now, I'm going to, it didn't tell, all it said is that 8 a.m. is high tide. Well, here's what I'm going to do. I'm going to start my graph at high tide, and I'm going to say that 0 is the same thing on my time scale as 8 a.m. You don't want to put times on here. You want it to be hours or minutes or something like that. And then kind of have a reference where you can reference. So if 8 a.m. is 0, well, 3 would mean 3 hours after 8 a.m. So that would be at 11 a.m. in the morning. 6 would be 6 hours after, because 0 is 8 a.m., 6 hours after 8 a.m. So we're going to have to translate that here into a time in a little bit. We'll get to that in a moment. All right, so let's start at high tide. There's high tide. I'll switch colors here. So high tide at 8 a.m. There's 8 a.m. Then it should go. So now think of how the water level goes. It's at high tide, low tide, back to high tide. So we're going to make that pattern. High tide should be back at high tide here. Halfway through, you should be at low tide. There and there. There would be one path of high tide back to high tide. So it's at high tide, drops to mean sea level, low tide, water level starts to rise again, and once again hits high tide, and then the pattern would start over again. Let's build a function. So this time, I think the one good thing, the sinusoidal is already where it should be because it's 6.5 above, 6.5 below. The amplitude would be that distance, which is 6.5. Period is 6. Therefore, 360 over k always has to give you the period. So k is 360 over 6, which is going to have to be 60. Here's your k value. Here's a function. y equals I'm going to go positive cosine, because if I go positive cosine, there's no phase shift. It's up at the high point to start. Amplitude is 6.5. Cosine. K value is 60. T, no phase shift. Vertical shift, none of that either, because it's already at 0. There's a function to model that blue graph that I've just drawn. Now, I need to figure out 1:47 p.m. 1:47 p.m. is how many hours along this scale. So remember, 0 was 8 a.m. So I need to figure out how much time is this after 8 a.m. Well, we can use finger math if you want. 9, 10, 11, 12 a.m. Then it's going to hit 1 p.m. So it's 5 hours and 47 minutes. 5 hours and 47 minutes along my scale that I've created. I would have 1:47 p.m. Well, I need to make that into an actual fraction. So 5 hours on my scale, it would be 5 and 47 over 60. Now, tides aren't moving real fast, so this one you could get away with rounding off if you wanted. So if I go 47 over 60, I get 0.783. So if you carried 3 decimal places here, you'd be okay. It's only if something's turning really fast that you've got to be careful with rounding. So here I can get away with 5.783. So if you went 5.783 hours after 0, that should put you at 1:47 p.m. So you're going to go over here, fill that in for T, and you should get where the water is in reference to mean sea level at that time of day. 5.783. This one's easy enough. I don't need to pause. Let's type this in our calculator. So it's going to be 3. Find the cosine of that. 5 by 6.5. And I'm getting 6.333. Y would equal 6.33 meters. So that means because it's positive, it's above mean sea level. So at that point, it is close to being high tide, right? Because high tide is 6.5. So we are at that distance above mean sea level at 1:47 p.m. All right, I got one more. Next one, actually, I'm gonna, yeah, we will look at, I'm gonna skip that one. I'm gonna go to the next one, the one on biology. So the other way that we will see these, I just want to get rid of this for a second here, is where they give you what are called key data points. Key data points need to be high points, low points, midway points. In this one, it's talking about populations. Now, here's what will happen sometimes in biology. Over time, what will happen is an animal or a plant or an animal or a fish population will increase. Measures may be put in place to get that population to go down, and the population will drop off to a low point, and then they'll take those measures away, and then all of a sudden the population goes back up again. And if you kind of model it out over a long haul and look at it, it would actually be modeled with a nice sinusoidal wave. Now, it wouldn't be perfect, but generally speaking, you might get a sinusoidal wave to model your situation. So we're going to assume that this population is going to model periodic sinusoidal behavior. It says, we're talking about the population of foxes. It's at a minimum number of 200 foxes at 2.9 years after they started. So T equals 0 is when they kind of started taking records. So what was happening is the population was going down, and then 2.9 years after they started recording the data, they hit an all-time low of 200. Then, all of a sudden, the fox population started going up again, and it reached an all-time maximum of 800 at 5.1 years. What we're going to do is model that data on a graph. So it's not, if you think, you may say this is very different. We started out with things that were clearly cyclical in pattern because they looked like circles, wheels and Ferris wheels and that kind of thing. Well, the last couple have been phenomenon science that aren't necessarily, when you look at them, a circle, but when you model their behavior, they are definitely circular in pattern. So I'm going to give myself a grid here. All right, so what do I know? I've got, now this, again, this is a little bit different. They give you key points. They don't give you how long it takes to make a full pattern. Well, this graph is going to start the pattern. I'm going to start it at 2.9. And the reason I'm starting it there is because it told me it was at an all-time low at that particular time, and that low was of 200 fox. So this is going to be my time axis, as always, in years. And this is going to be my fox population. It says the next maximum. It doesn't say any old maximum. The next maximum, so meaning as time passes, the next maximum happened at 5.1 years. And that at a maximum of 800 fox. So we had a low point. Now we've got a high point, which means that's half of a wave. Now we're going to let you even get away with just that. So max, high point. So what you got to figure out is, well, what did it take to get to here? 2.9, so 3.9, 4.9. It took 1.2 years to get from there to that maximum. If this is sinusoidal, it's going to take the same amount of time to get back to where it started, which would be another 1.2 this way, which you had to figure out by looking at these two times they gave you, which now means this will be 5.1, so 6.3. Oops, 6.3 would be that time, and it should be back down here. So now your population is going to model sinusoidal in nature. This is not scaled off, so here we should, in this case, put a compression bar there and make sure that you don't extend over and hit the axis over here, because we don't know unless we had this scaled off nicely, which we're not. We're just using this as a rough sketch to get our function. Well, if this is 200, this is 800, I need to figure out the middle. So I need to figure out what's halfway between 800 and 200. Well, all you got to do is take 800, basically get the average of them. 800 plus 200 is 1,000. 1,000 divided by 2, this has got to be 500. Now let's see if that makes sense. 300 that way, 300 that way. Makes sense. I'm in the middle of the wave. Freehand in this one, which means I've got a vertical shift of up 500. I have my amplitude of 300. Right, amplitude is from there to there. Amplitude is 300. I'm going to pick negative cosine for my function, and now I'm going to get my k value here. So y equals, let's do this first. So 360 over k equals the period. It started at 2.9. Oh, I messed this up. Let me look at this. This should have been 2.4, not 1.2. 2.4 to get from there to there. This should have been another 2.4. So that's not going to be 6.3. You got to fix that. See, this is what happens when you don't have students in front of you to help you. This would be 7.5. This should be 2.4. The same as this, 2.9, 3.9, 4.9. Yeah, no, 2.2. My goodness. Not 2.4, 2.2. It's going to change these. At least I fixed it now anyway. So that's 2.2. That's 2.2. That would make this 7.3 there, which gives me a period. So from here all the way over until I get to that low point again would be 4.4. So K would be 360 divided by 4.4. I'll see if it goes evenly. Again, it's not something that's spinning in a real fast circle, this pattern, so rounding off a little bit here won't hurt us. 81.8181. You know what? Just to show you what I mean, I'm going to leave, this doesn't go evenly, I'm going to leave it exactly as this. That's my K value. So when I build my function, just to keep everything as accurate as possible, and here it's going to be, so switch colors. Y equals, I'm going negative cosine. Amplitude, I said, was 300. Negative 300 cosine. K value is 360 over 4.4. T, for a negative cosine, you got to shift to the right 2.9. So right 2.9. Vertical shift is up 500. This one, now this one gets in, it's asking find two different times when the fox population is 625. I'm actually going to leave that for the next video that I make. That's kind of the last thing in the unit we got to learn how to do. So all we would now do is, let's say I wanted the fox population after, let's just check, after 7 years. Fill 7 in here for T. Put that in your calculator. I am going to pause this one. It'll take me a while to type that in. All right, so after tapping some buttons there in the calculator, I came up with this number, 227. 227. Now, because we're talking about fox population, we're not going to get into decimals. We're going to approximate, so I'll just say with a dot over it. And if you were to do this in any kind of a biology study, these aren't going to be exact. It's not going to be an exact pattern. It's going to be close. You'll get data that will model the pattern. So anything we do here is going to be an estimate of the population. So based on our mathematics, we would estimate the fox population to be somewhere in the vicinity of 227 after 7 years have passed. Now, I just want you to look at your graph and see if that answer makes sense. If this is 7.3, well, 7 should be somewhere over here. So if I go up, I hit the graph about there. If I came across here, I'd be pretty pleased with my estimate. It's slightly above 200. So it appears that everything we've done has worked out correctly. So that leaves, as we said, the question that they asked about what if the population is a certain number? How do you figure out years when it's at that number? That's going to be the last thing we look at in this unit. All right, so I'm going to end there and get you some practice questions now on this material.